Welcome to section 2.1, Basic Set Concepts. Objective 1, use 3 methods to represent sets. So a set is a collection of objects whose contents can be clearly determined. The objects in a set are called the elements or members of the set. A set must be well defined, meaning that its contents can be clearly determined. Sets can be designated by word descriptions, the roster method, and the roster method is just a listing within braces, separating elements with commas, or set builder notation. An example of set builder notation would be a brace X, vertical line, and then conditions. This would be the set builder notation, where the braces mean the set of what? All elements of X, the vertical bar, such that, and then the conditions, X meets these conditions. Okay, so that's how you would state a set builder notation. So let's do some examples here. For the first one, we're asked to write a word description of the set S equaling Washington, Oregon, Idaho, and Utah. Well, a word description would be something like the set S is the set of 4 states in the Northwest region of the US. Okay, because Washington, Oregon, Idaho, and Utah are all in the Northwest region of the US. B, set B is the set of US coins with a value of less than $50. Express this set using the roster method. And remember, the roster method is just writing out all of the elements within braces. So our set B is going to be the value, or the set of coins whose value is less than $50. So that would be a penny, a nickel, a dime, and a quarter. Okay, so that's the roster method. C, write a word description of the set 1357, comma, dot, dot, dot. So it's going to continue on with the same pattern. Okay, now 1, 3, 5, 7 are all odd numbers, but what type of numbers are they? They are considered natural numbers. So this would be the set of odd natural numbers. Okay. D, express the set using the roster method. So again, listing out all of the elements within braces. So we have a set O, and this is equal to the set of all elements of X such that X is a positive odd number less than 10. So O, set O, in the set written in the roster method would be 1, 3, 5, 7, and 9, because those are all of the odd numbers less than 10. Okay. All right. Objective 2, define and recognize the empty set. So the empty set or the null set represents or is represented by these bracket or parentheses here, or the null set, which is I guess you could say a 0 with a slash through it. All right, so this means that a set contains no elements within it. So notice that the parenthesis and the circle with the slash through it have the same meaning. So you could see either one. However, the empty set is not represented with both of them combined. This notation represents a set containing the element of the empty set. Okay. So let's look at some examples here. Which of the following is an empty set? And remember, an empty set is a set that contains no elements. So for the first one, we're looking at all X values such that X is a number less than 3 or greater than 5. Well, in this set, we have numerical values, numbers that are less than 3, like 1, 2, 0, or greater than 5, like 6, 7, and 8. So this would not be an empty set. And remember, it is not the empty set because it contains elements. So in our next set, we're looking at all X values such that X is a number less than 3 and greater than 5. So we're asking ourselves, is there a number that is less than 3 and also greater than 5? And there is no such number. So that means this set contains no elements. So this is the empty set. Okay. C, nothing, just nothing. All right, so nothing is a descriptive word. It is not a set. All right, so this is not the empty set. And D, we spoke about this previously, but we have the empty set within a set, which means that this set contains an element, which is the empty set. So this is not the empty set. So out of all of these options, B would be the one that is representative of an empty set. Okay. Objective 3, we're going to use two new symbols here. They look like E's, but they actually mean something else. So the symbol of the element is used to indicate that an object is an element of a set. So this symbol is used to replace the words is an element of. The symbol is an element of with a slash through it is used to indicate that an object is not an element of a set. So this symbol replaces the words is not an element of. Okay, so let's look at some examples. Here we're asked to determine whether each statement is true or false. So we're given an element and we need to determine based off of the symbol whether it's an element of the set or not an element of the set. So for A, it's saying 8 is an element of the set 1, 2, 3, dot, 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 10. Okay, so here the dot, dot, dots would mean all of the values that are between 3 and 10 that follow the same pattern. So for this problem or statement, this would be true because 8 is between 3 and 10. And if we were to count it all the way through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we would land at 8. So 8 is an element of this set. B, R is not an element of the set A, B, C, and Z. And this is true. R is not an element of the set. R is nowhere to be found in these 4 letters. So therefore, it is not an element. Monday is not an element of the set X such that X is a day of the week. Well, this is false because Monday is a day of the week. So that means it is contained in the set. 12 is not an element of the set 1, 2, 3, dot, 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 14. So we're continuing on between all the numbers that follow the pattern between 3 and 14. So this is true. 11 is not an element of the set 1, 2, 3, dot, 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 9. So we end at 9. So that means 11 is not contained within that set. So this would be true. And then the set 3 is an element of the set 3, 4. Okay. So this is an example where it's asking if a set is within a set. And in this case, the set 3 is not an element of the set 3, 4. So this would be false. In order to make this true, this set would have to contain 3 as a set within a set. Okay. Objective 4, apply set notation to sets of natural numbers. So the set of counting numbers is also called the set of natural numbers. And can be written as the set n equals 1, 2, 3, 4, 5, and so on. Those 3 dots or ellipses indicate that there is no final element, all right, and that the listing goes on forever. Okay, so inequality symbols summarized in table 2.2 in the text on page 55 are frequently used to describe sets of natural numbers. Okay, so I recommend that you review those inequality symbols. But let's look at some examples. Express each of the following sets using the roster method. So remember, the roster method is listing out each of the elements, separating them with commas within braces. So A says set A is the set of natural numbers less than or equal to 3. So we want all of the numbers, all the natural numbers that are less than or equal to 3. Okay, and natural numbers start at 1. Okay, so that would be 1, 2, and 3. All right, for B, set B is the set of natural numbers greater than 14. So we're not equal to 14, we have to be greater than 14. So we'll start at 15, 16, 17, and then it will continue on forever. And then C, set O equals the set of X values such that X is an element of the natural numbers. So N here represents the natural numbers, and X is odd. Okay, so set O, written using the roster method, would be all the natural numbers that are odd. So that would be 1, 3, 5, 7, and so on. Okay. Objective number 5, determine a set's cardinal number. Now, the cardinal number of a set A, n of A, written like this, is the number of distinct, this is key, distinct elements in set A. So repeating elements in a set neither adds new elements to the set nor changes its cardinality. What does that mean? So if I have a set A and A has the elements 3, 5, and 7, and I have a set B and B has the elements 3, 5, 5, 7, 7, 7, we would say that the cardinal number for set A would be 3 because set A has 3 distinct elements, 3 different number values. Now, the cardinal number for set B would also be 3. Even though 5 and 7 are represented many times, it doesn't change the number of distinct elements that are within set B. Therefore, the number of elements in A is going to equal the number of elements in B. All right, let's do some guided examples. So here we're asked to find the cardinal number of each of the following sets. So for the first one, set W, its cardinal number will be 5 because we have 1, 2, 3, 4, 5 elements. For B, the cardinal number for set S would be 1 because we only have one element. C, the cardinal number for Y would be all of the elements contained within this set. And so we see that the numbers are increasing by 1, 9, 10, 11, then 15, 16. So we would want to know how many elements are between 9 and 16. So 9, 10, 11, 12, 13, 14, 15, 16, and that would be 8. For D, we want to know the cardinal number for P. Okay. Now P equals the empty set, and there's no values or elements within the empty set, so this would be 0. E, we want to know the cardinal number for set Z. So again, counting how many elements are within that set, and that would be 5. Okay. F, the cardinal number for set R. We are going by 2, 4, 6, all the way up to 30. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, all the way up by 2s. So we would have 15 numbers. G, the cardinal number for set K, all X values such that X is a day of the week that begins with the letter A. So how many days of the week begin with the letter A? 0. So that means the cardinal number would be 0. And then H, the cardinal number for set E is the word 5. So that means we have one element in this set. All right. Objective 6, recognize equivalent sets. So equivalent sets have the same number of elements or the same cardinality. So a 1-to-1 correspondence between sets A and B means that each element in A can be paired with exactly one element in B and vice versa. So if two sets can be placed in a 1-to-1 correspondence, then they are equivalent. Meaning the cardinal number of set A will equal the cardinal number of set B. Okay, so let's apply this to an example. So in the figure here to the right, figure 2.2, it shows the percentage of Americans optimistic about the future for each region of the country. We are going to let set A represent the set of the 4 regions shown in this figure. And then set B, we're going to let this set be the percentage of Americans in each region optimistic about the future. And we need to answer, are these sets equivalent, and explain. Well, let's first list off the values in set A. So set A is the set of the 4 regions, and the 4 regions are West, Midwest, South, and Northeast. Okay. For B, the set of the percentage of Americans in each region optimistic about the future. So this would be 75, 73. And now we don't need to write another 73 because we want distinct elements, because we'll use the cardinal number to determine whether they are equivalent. Okay. And then 68. So the cardinal number of set A is going to be 4, and the cardinal number of set B is going to be 3. Now, these two do not equal each other. Okay. Therefore, they're not equivalent. Okay. So to answer the question, no, because the sets do not contain the same number of distinct elements. Okay. All right. So remember, in order for you to have equivalent sets, the sets have to have the same number of elements, okay, or the same cardinality, meaning their cardinal number must be the same. And the cardinal number is determined by the distinct number of elements in each set. Okay. All right, let's do a couple more. We need to determine if these two sets are equivalent. So S and T, are they equivalent? Well, the cardinal number of set S is 5, and the cardinal number of set T is also 5. So that means the cardinal number of S equals the cardinal number of T. So then yes, they are equivalent. So yes, because both sets contain the same number of distinct elements. Okay. All right. And B. So we have set O and set P. So set O says all x values such that x is an element of the natural numbers and x is greater than or equal to 6 but less than 9. So that means if we were to write this using the roster method, set O would consist of the numbers 6, 7, and 8. So this would give a cardinal number of set O equaling 3. For set P, all x values such that x is an element of the natural numbers and x is greater than or equal to 9 but less than 13. So this, using the roster method, would be represented by the elements 9, 10, 11, and 12. So the cardinal number of set P would be 4. So the cardinal number of O does not equal the cardinal number of P. Therefore, they are not equivalent. So in a complete sentence, no, because the sets do not contain the same number of distinct elements. All right. Objective 7. Distinguish between finite and infinite sets. So set A is considered a finite set if the cardinal number of A equals 0. That is, A is the empty set, or the cardinal number of set A is a natural number. A set whose cardinality is not 0 or a natural number is called an infinite set. Okay. So in our examples here, we're asked to determine whether each set is finite or infinite. So for the first one, we are looking at all x values such that x is an element of the natural numbers and x is greater than 2000. So are we able to identify the cardinal number of this set? We want all of the numbers that are an element of the natural numbers, so that's all the counting numbers, and they are greater than 2000. That's a lot of numbers. That's going to go on forever. So this would be an infinite set. Now B, the set of natural numbers less than 100. Well, this is a set of numbers we can actually count because the natural numbers starts at 1 and we want all the numbers less than 100. So it would be from 1 to 99. So this has a start and an end. So this is a finite set. All right, objective 8. Recognize equal sets. So equal sets have exactly the same elements, regardless of order or possible repetition of elements. If two sets are equal, then they must be equivalent. For example, if we were asked to determine whether this statement is true or false, the set 1, 2, 3 equals 2, 3, 1, we would note that the sets 1, 2, 3 and 2, 3, 1 contain exactly the same elements, 1, 2, and 3. Therefore, the statement 1, 2, 3 and 2, 3, 1 would be considered true. Now, equal and equivalent in the English language tend to be interchangeable. However, in set theory, that is not the case. So equal sets contain the same elements. Okay, that's key. Equal sets contain the same elements, while equivalent sets contain the same number of elements. Remember, in the previous objectives, in order to determine if something's equivalent, the two sets, we would have to look at their cardinality. Okay, so that means if two sets are equal, then they must be equivalent because they have the same elements. Okay. However, if two sets are equivalent, they are not necessarily equal because if you're equivalent, right, you want the distinct amount of elements, but that doesn't mean that you could have repetition, but it doesn't play into the cardinality, but it does play into its equality. Okay. So, guided example, determine whether each statement is true or false. So in our first one, we have this set OLD, and we want to know, is it true that it's equal to DOL? And this is true because they both have 3 elements and both sets have the same elements as well, regardless of order. B, we have the first set 4, 5, and the second set 5, 4, and the empty set. So this would be considered false because the second set has an element that is not contained in the first set, which is the empty set. Okay. All right. In these exercises, we need to state whether these sets are equal and explain. So for C, we have set M and N. Okay. For M, we have 1, 2, 3, 4, 5, and N, we have 0, 1, 2, 3, 4. Now, both of these sets do not contain the same elements, and that is a requirement in order for it to be equal. So no, these sets are not equal because both sets do not contain the same elements. Now, are M and N equivalent? Yes, because their cardinal numbers are both 5, but they're not equal because they don't have the same elements. Okay, and then D, E and F. E has 1, 1, 1, 2, 2, 3, 4, and F has 4, 3, 2, 1. So this would be yes, because both sets contain the same elements and the same number of elements. So in order for it to be equal, they have to have the exact same elements, and they both do. They both have 1, 2, 3, and 4. Regardless of order or repetition, they're equal. Now, are they equivalent? Yes, they are also equivalent because they both have a cardinal number of 4. Remember, equivalency is based off of the distinct number of elements that is within the set, regardless of repetition. Okay. All right. That concludes section 2.1.